Good morning, everybody. That was pretty good, but we can do a little bit better, right? Good morning, everybody. That sounds like a big auditorium. Welcome to Pushing the Limits of Windows. My name is Mark Russinovich. How many people have been to one of my previous 2 sessions here at TechEd? How many were in the last session with Manasseh? Do you like that session? Yeah? Okay. Well, this session, completely different type of session than the last one. I'm going to go ahead and skip that slide. This one is about resource exhaustion, the limits of Windows. Specifically a few limits that we're going to cover this morning. The reason that I think it's important for people that are using Windows systems, managing Windows systems, whether it's your home systems or systems at work and everybody's their own home IT administrator for your family and friends, that when Windows ends up running into the limits, and it's applications that are pushing the limits of Windows, you start to get undefined, bizarre behaviors. At the minimum, you're going to have an application that crashes or hangs. So it's a service outage. And that's something that obviously if you've got a mission critical system, you don't want. If you've got clients, users that are using particular applications, if those applications constantly are running into problems, that's also going to cause you a headache. In the worst case, though, it actually can cause data corruption. If an application crashes because it's out of some resource or this operating system's out of a resource, that means that typically any data that is modified, not yet saved or committed, is going to be lost unless it's got transactional semantics. It might even end up corrupting its data store. So obviously you want to avoid resource exhaustion. Another aspect of knowing the limits of Windows is capacity planning. If you understand how much virtual memory a particular machine has, and you understand how to measure the virtual memory requirements of a particular application, you can be confident that this application actually fits nicely on this particular computer. Most of the time, though, administrators are just configure a machine. Yeah, it seems like it's about right with 4 gig of RAM and 4 gigabyte page file. Run SQL Server on it. Let's see what happens. Let's measure the performance of SQL Server. And you kind of look anecdotally from the outside without really understanding what's going on inside the system to affect the performance of SQL Server. And maybe adding some more RAM might improve the performance of SQL Server. There's ways for you to be able to figure out if that's the case. Systems monitoring, again, if you've got a bunch of systems you're managing, you want to know the health of those systems. You want to know how close they are to the limits. You want to be able to address a problem before it actually becomes a problem. If you see a particular mission critical server running low on available memory, you know that's going to start running into performance problems. You want to step in and mitigate that before it gets to be a real problem. And of course, troubleshooting. When something does go wrong, when somebody does start to hit limits, when you suspect an application's pushing Windows too hard, being able to go in and confirm it by understanding where to look to verify that that's the case is important. So in this session, what I hope you're going to learn, what I'm going to try to share with you, is an explanation of some of the core kernel limits, where they come from. Some of them actually come from hardware. Some of them come from the Windows architecture. Some of them come from licensing. So you understand for a particular version of Windows on a particular box where those limits are coming from and what they are. And in the process, in just terms of practical knowledge, because knowing the limits is all well and good, but what can you do with it? I hope to teach you how to troubleshoot handle leaks, which is a common resource exhaustion scenario. How many people have run into a problem on a server as a problem with resource exhaustion with handle leaks? How many people didn't know you did, but you really did? Okay. What I hope to do is also define some standard memory terminology, and this is kind of really sad state of affairs when it comes to Windows and memory management and the terms that we use. And the terms that are used in the tools in the box, the terms that are used in the books, there's inconsistencies all over the place. And those inconsistencies make it so that one person says something, the other person hears a different thing. And it's impossible to communicate effectively. Also, it's impossible to say, you know, I see this value on this tool. What value does it correspond to in this other tool when the terminology is completely different? I've actually given a talk on memory analysis at Microsoft in an effort to try to standardize Microsoft internally on common terms for memory limits, for memory values. And I'm going to present that and share those values with you that seem to be accepted within Microsoft and what we've used in the book and the Sysinternals tools. I'll teach you how to spot a memory leak. So this is a most common way that an application runs into a resource exhaustion is leaking memory. And when you leak memory, you hit a particular limit and the application falls over. How can you spot a memory leaker before it starts to cause a problem? One of the most critical things that an IT administrator has to do is answer the question, how big does the paging file have to be? How many of you have asked yourself that question or been asked, how big does the paging file have to be in the last, say, 6 months? So it's a burning question. I'm going to give you the answer, the definitive answer on how big your paging file should be. 1 gig. That's it right there. No, just kidding. And I'm going to tell you how you can figure out if you've got enough physical memory on your system. Obviously, most of the time the answer is no. Too much memory is never a problem. But really, when you're sizing up your servers, how much are you oversizing the server? Are you oversizing your clients for the workloads that are going to be running on them? Are you undersizing them? How do you figure out if there's enough physical memory on the system for it to run effectively? I'm going to be using a tool called Test Limit, which I wrote for the Windows Internals book. The Test Limit supports like 10 different options to stress different limits in Windows, stressing handles, stressing virtual memory, stressing locked memory, stressing the number of processes that can be created. And I wrote that tool because it's fun to just watch Windows blow up. But no, really I wrote it because some of these limits you just have to go verify experimentally. You say, well, I know the source code says this. I know that this is what the documentation says. Let's go see what happens when we try to hit that limit. And you might run into other limits before you hit the one that you're after. So here's the outline. I'm going to cover handles, like I said, virtual memory, and then I'll cover physical memory limits. There's a lot of other limits that I could potentially cover. I'm going to point you again at this resource at the end of the session, and that's my blog post series that this talk is named after, called Pushing the Limits. I started that blog post series about a year ago. There's roughly 8 posts in the series, and they cover physical memory, virtual memory, handles, processes, threads, GDI objects, user objects, page pool, and non-page pool. Obviously, you can see that I don't cover processes and threads limits here, page pool or non-page pool limits. What I've done is pick the limits that I think are most interesting to people, what are most practical. Definitely, there's people in this room that have run into problems when non-page pool or page pool has been exhausted, and sure, it would be interesting to go share with you how to go track down the problems with non-page pool or page pool leaks, what the limits are around non-page pool or page pool. Unfortunately, I've got 75 minutes, so I've had to pick and choose. How many people, by the way, have read at least one of the posts in the Pushing the Limits series? So it's surprisingly few of you. So I'll wait now while you go read the posts. I encourage you to do that. But let's get started with looking at handles. Now, everybody's heard the term handles, but what is a handle really? Windows defines in the operating system kernel a number of different types that represent operating system resources that applications and drivers can reference and create. The way that you can see the handles types, the types of objects that handles can be created for, is to run the Sysinternals Winobj utility. And this is Winobj running, of course, on Windows 7, or it's actually running on Server 2008 R2. Let me zoom in here. And you can see that there's a whole list of different operating system resource types. Some of them you've probably never heard of. A lot of them are used internally. There's no way to access them or create them using documented public APIs, but they're, of course, important to the way the system operates. A desktop, for example, is probably, you know what a desktop is. It's actually what I'm looking at now, and you can have multiple desktops active on a same Windows station, Windows station being another particular here, another particular object defined by the window manager. And then there's the ones that are just obvious, a process. So there's a process type in the kernel. And what happens when you create a process is that an object is instantiated of this type. The type object is the template for what a process is. It defines the data structure for the process, and it allows the system to do reference counting on the object as well. So a process will actually get deleted when the last reference to the process object, an instance of this object right here, is released. How many object types are there? It varies across operating systems. Every operating system, there's more and more. In Windows 7, there's 42 object types. There's obviously no need for any more. It's the answer. Well, how does an application then interact with these resources? There's APIs for the publicly documented ones to be able to instantiate them. For files, for example. There's a create file API. For processes, there's the create process API. What you do with one of those APIs is you specify some characteristics, attributes for the object that you want to create. I want to create a process. Please make it suspended. I want to have it this priority. I want it this current working directory. The process subsystem goes and defines an instance of the process object with those characteristics. The programmer wants to get back some way to reference, to perform further actions on that particular object. One of the things that the kernel could do is just simply return a pointer, but that wouldn't be very safe. What it does then is returns an indirect reference to the object that was created, and that is the handle. Now, a handle, what it really is an index into a table. Every process has a handle table. The handle returned is simply the index. From the programmer's perspective, it's an opaque number. They're not supposed to actually do anything with it or look at it. But what they can do is if they want to interact with that object again, they pass the handle to a subsequent call. So if I want to suspend the process, I call suspend process. I pass in the handle. When the handle's passed into the system call, the kernel knows what object you're talking about because it looks in the process handle table at that index. It finds this entry here, an entry in the handle table. That entry has a pointer to the object, and it can go find the process object then and do the suspend operation on it. You see that there's another attribute in that handle table entry, and that's the access. Another benefit of doing this, creating an object or referencing an object and then returning a handle but keeping the object around, is that the programmer, the system, doesn't have to go through a security check on the access control list every time the programmer wants to do something to the object. We don't have to do an access check when the programmer calls suspend process on that process object. Instead, what the programmer is expected to do is ask for all the accesses they want to perform on the object up front at the time they call create process or create file. If the open is successful, if the security check passes and the parameters are all correct and we actually create an object, handle table entry is created, pointer to the object, and then cached there are the accesses the programmer is granted, the program's granted. When they call suspend process, then the system looks at that access mask and sees if the suspend process right was asked for and granted at the time the object was open. If it wasn't, the programmer is going to get back access denied. If it was, then it's obviously going to proceed. So that's the benefit of the handle table. What happens, though, with handles is that there's a limit on them, of course, and applications that leak handles can run into this limit or other limits associated with the creation of objects and the handles that reference them. Let's go see. I'm going to fire up a VM here. I've got an XP VM. Wait, it's rebooting for some reason. I'm sure updates have just been applied to it. Let's go to our Win7 VM instead. And I'm going to run test limit -h. And what this is going to do is just simply try to allocate as many handles as it can. It's creating event objects for each handle. We're at 4 million, 5 million, 6 million, 9, 10. It's pretty impressive, isn't it? So this is going to bottom out around 200 million, so let's just wait until then. Actually, it stops right here, 16.7 million, something like that. You're going to see the same limit on any version of Windows that you run on. This is 32-bit, or sorry, 64-bit Win7. I could have done that in a 32-bit XP system, and I would have gotten the same answer. That limit comes from the fact that the handle table that's created for the process has a certain number of entries. It's actually a 3-level table that's created, and there's a fixed number of entries in that top level that's kind of determines the full size, if it's fully populated, because it's a sparsely populated table, can get to. And that happens just to be around 16.7 million. So that's one of the limits related to handles. There's another limit related to handles, and that's the amount of paged pool just for storing those handle tables. Handle tables are allocated on a page-by-page basis, 4K page. But a handle table entry varies in size on 32-bit and 64-bit. It's 8 bytes on 32-bit, 16 bytes on 64-bit Windows, and that will cause a penalty on paged pool. In addition, if you've got a process leaking handles, there's two ways that it can leak handles. One is referencing the same object it's already got. So if it's opening a particular object, like a named event, and it opens it over and over and over again, and it fails to close the handle after it opens, before it reopens it again, you've got a whole bunch of handles pointing at the exact same object. So you're just leaking handles, you're not leaking objects. The other potential problem is that it's creating new objects, and really is when it's done with the previous one, it's not closing it and deleting it. So it could actually be leaking not just handles, but the objects themselves. Let's go take a look quickly at our VM, and we can see just how much stress on paged pool, wrong VM, paged pool. Actually, we need to run ProcessExplorer, don't we? How much page pool penalty has been caused by just creating these handles. And page pool is a finite resource, like I said, has a typically stricter limit on Windows XP than Win 7. You're going to understand in a little bit why this Win 7 machine is a little bit slow. It's a VM. I've got 4 gigabytes of RAM on this laptop, and so I've got 2 VMs going. I need to be careful about how much RAM I give the VMs. And actually, we might have just had a failure here. Oops. Which I hadn't seen before. So it looks like the system's locked up at this point. And that's because we probably did hit the page pool limit and exhausted page pool. So there, I didn't mean to show you the page pool limit, but sometimes you just happen to hit it. And so let's reboot this thing. And just trust me that there's a page pool penalty. So what do you do? How do you detect a handle leak, first of all? And how do you figure out what process is leaking handles, and then what handles they're leaking? How many people support line of business apps? And when you find line of business apps on your network misbehaving, the developer expects you to come and tell them exactly what's wrong. Like, you can't just say your app is broken, or it's throwing me this error, it's crashing. They're like, what? Prove it's my fault. So here's the tool for being able to prove that it's actually a handle limit problem. There's a number of ways you can see how many handles processes have open. One of the ways is with ProcessExplorer, adding the handle column here, which gives you a count of the number of handles processes have open. Task Manager also supports adding a handle count. And one of the things that I always recommend you do when you're supporting Windows systems is actually look at your systems on your network for kind of what's baseline expected behavior. You can see here on this system that the process having the most handles has 1,500 handles, which right there tells you, okay, 1,500 is kind of a nominal number of handles, kind of max that I should expect to see. If I see a process with tens of thousands of handles, that's likely a problem. It's probably leaking. The thing is with handle leaks, like any other leaks, is they can be insidiously slow. So this thing can grow over the matter of weeks and eventually end up keeling over your server. One of the things that people like to do is set up alerts using perfmon on things like handles for their mission-critical applications. ProcessExplorer will let you actually see into the handle table of a process. Let me launch, for example, Notepad. Oh, actually, let's start command prompt. A little bit better demo. Here's the command prompt process. I'm going to open the handle view down here below. And what this is showing me is the list of handles that command prompt has opened to objects that have names. Now, what we're not seeing is the list of objects that don't have names. We can see the full list of objects if we go to View, Show Unnamed Handles and Mappings. And now we can see additional objects that command prompt is open that are unnamed. Most of the time when you're looking for a handle locked issue, you're going to be looking for something that's named, and that's why ProcessExplorer only shows you the named objects by default. You can see there's handles to files, to registry keys, to the Windows station it's on, and to command prompt's one and only thread. If we change directories, so this file right there, demo, is command prompt's current directory. It's got an open handle to it, which is why if I tried to delete that directory from someplace else, I'm going to get an access denied, because somebody's got a handle open to that particular directory. System won't let it get deleted. If I change directory, you can see ProcessExplorer shows me in, well, you saw it in red, the handle being closed, and in green, the handle that was open. It does that to highlight the differences between different refreshes. Red, objects that are gone. Green, objects that are new to the current refresh. So if you suspect a handle leak, you see the handle count going up, you can actually go and figure out exactly what's leaking in this way. Dave Solomon actually ran into this problem on his own laptop. It was made by a Japanese computer manufacturer that likes to put additional value-added software on their laptops. And every couple of weeks, he'd have this thing running, and suddenly it'd run out of page pool and die. It'd just hang like the way we saw it. He started to look with tools like, actually he uses ProcessExplorer, figured out that it was a handle leak in a particular one of these little applets. He was able to go and see, using the handle view, exactly what handle was leaking, and send an email to the manufacturer saying, you've got a bug in this particular application, it leaks this handle at this rate. And the manufacturer actually was nice enough to respond and say, okay, we forwarded this to our team, they acknowledged the bug, and it's going to be fixed. So that's a successful case of handle troubleshooting. One of the things that you can do to figure out exactly where in an application a handle is being leaked, and this is interesting for people that are developers because it's sometimes easy to lose track of the resources you've got. Where am I leaking these resources? Where are these handles being created? Also, if you're looking at those line of business applications, where are they going to be leaking things? Is to turn on handle tracing. And there's a few ways you can do that. One is using the Application Verifier tool, which is a free download from Microsoft. And the other way is just to do it right from Windbg, which is the most convenient way, I think. And that's what I'll do right here. Is launch command prompt under the debugger, turn on handle tracing, and then press go. And now that command prompt, if I change directories, just like we saw before, we know that at least one handle is closed and another one's open. If I do control break and do htrace, this shows me every single handle related activity that happened during that time. One of the things that we see here are a bunch of handle activities from, here's the change directory right there. Find, fix, and run, change working directory. So this is the handle that we just saw get created. We're also see here lots of handle operations from just DLLs loading and opening things. So here's, I didn't know that we had a Windbrand DLL, but there's a Windbrand DLL that command prompt calls into that opens a handle. If you just want to see the difference, like in terms of what handles are created now that weren't created at the time of the previous snapshot, these are the open handles that were created in the intervening time frame. So that's really the best way to get a handle on your handle leaks. Let's turn our attention now to virtual memory and talk about limits related to that. The most fundamental limit to a process's ability to allocate virtual memory is its own address space. A process can run out of address space, and that means that even if the system has plenty of capability to allocate more virtual memory, the process itself is stuck. This is typically only an issue on 32-bit processes, as you'll see in a second. But the second major limit with virtual memory is the total amount of virtual memory available on the system, and that's called the system commit limit. At least that's what I call it, the system commit limit. So let's take a look first of all at address spaces. There's two address spaces that we're got to consider when we look at 32-bit OSs. The first is the default address space. So this is a default 32-bit process. The address space is split in half. In the high end of the addresses, which is shown on the bottom of the screen by computer scientists, we've got the system address space. And on the top half of the screen, which are lower addresses, starting at 0, so 0 is at the top, is the user mode part of the address space. When you switch between threads of different processes on a particular CPU, Windows changes the page tables to reflect the address space of the process that you're switching to. And so that's why you see those layers up at the top to represent different processes. The system part of the address space is held constant, so it's mapped into every process's address space. So it's really the system is saying, I've got 2 gig to do whatever I want to do with, you've got 2 gig to do whatever you want to do with. 2 gig is potentially a problem in 32-bit server applications that allocate large amounts of virtual memory. Well, not necessarily a problem from performance perspective, not a correctness perspective. Let me give you an example. If I've got a SQL database, and that database is exactly 2.5 gigabytes in size. If I'm running with a 2 gigabyte address space, can SQL just suck the whole thing into its address space and reference it? No, it just doesn't fit. So what it's got to do is create mappings. It's got to do its own management of, okay, I've got these pieces of the database in my address space. Now I want to access this different part that's not there. I need to eject one of my mappings to another thing. So it's complicated, and that causes performance issues as well as it's doing its mapping and remapping of things. That's why the 3 GB switch was introduced in Windows NT SP3. This switch, when you boot /3GB, lets you move the line to 3 gigabytes, 1 gigabyte. In Vista, the user VA, in Windows Server 2003, the user VA switch was added, which lets you move the line anywhere between 2 and 3 gigabytes. 3 gigabytes being the most you can move it. What this does is obviously give the applications more address space. The downside of this is it gives the system less address space. This is particularly problematic on 32-bit systems prior to Vista and Server 2008 because they have fixed system address space where blocks of the address space are allocated for particular use, and once it's out of those particular regions, the system falls over. Whereas on Vista and Server 2008 and higher, you've got dynamic kernel address space where it can dynamically grow and shrink regions so it can better use the 1 gigabyte than previous versions of the OS. So the benefit here is purely a performance benefit. If an application fails to run without the 3 GB switch, the application's got a fundamental problem. It really should run in 2 gigabytes of address space, just should potentially run better in 3 gigabytes of address space. One caveat on this is that the application that wants to take advantage of that extra up to 1 gig in its address space needs to tell the operating system it knows how to do it, that it's grown up enough to do it. That, hey, I don't need the training wheels, you can take them off, and I know what I'm doing. The way that it does that is by marking itself in its program executable header, the image file header, that it's large address space aware. When that sees that, the operating system will let it access and allocate from that between 2 and 3 gigabyte line. Then we have the 64-bit address space. Obviously, theoretically, 2 to the 64th is 16 exabytes. It's a pretty huge number. We're never going to need more than that, right? If you look at the way Windows defines the address space on 64-bit Windows systems, it doesn't use the entire 16 exabytes. In fact, it uses just a very tiny part of that potential address space. 8 terabytes for user processes, 8 terabytes for kernel processes. We came up with that when the Office team was working on Office 64-bit. All right, really? Office jokes are getting tired at this point? And Itanium, of course, we got it. Anybody running Itanium systems, out of curiosity? So you saw that 2 months ago we said we're done with Itanium? Finally. Thank you. Virtual memory types. Within a particular address space, how does a process allocate virtual memory? One of the concepts, fundamental concepts that I like to convey is something called process committed memory. If you take a look at a process as address space, there's a type of virtual memory that it allocates that's committed. And what that means is that it's actually backed by data someplace. It's either backed by an executable image on disk, or it's backed by paging file. In other words, if we were to eject that data from RAM there's a place for it to go. Either the system can regenerate it from a read-only executable image, so we can toss out the copy of Notepad in RAM. We know how to get back a copy of Notepad into RAM from the file on disk. Or if it's private data that needs to be ejected, where are we going to write it to? The paging file. We've got to save it someplace, and that's exactly what the paging file is for, is to be able to take this private data that doesn't correspond to a file on disk and save it. It's kind of temporary data, that data that goes to the paging file. So committed memory is backed either by a file or by the paging file. There's other types. Within the committed type of virtual memory, there's two subtypes, shareable and private. I've just talked about private virtual memory. Process allocates virtual memory. It stores local variables and data structures in it. Private to itself. Can't share it with another process because it has to do with its own execution. And then there's shareable virtual memory. There's two types of shareable virtual memory. One is shared memory map files. So I create a file on disk. I say I'm going to share it with another process. We're going to communicate through this and share it. That's shareable process committed memory. I can also have shareable memory that's backed by the paging file. So this is kind of temporary shared memory. I create this shared memory section. I give it a name so another process can open it. And now we communicate through that. If the contents of that shared memory region need to be ejected from RAM, it goes out to the paging file. The other two types of virtual memory in the address space are reserved virtual memory and free virtual memory. Reserved is simply you saying, or the process saying, hey system, I want to allocate a big block of my address space, but I'm not sure what I'm going to do with it yet. But stay away from it. Don't allocate things out of it. I'm reserving the right to use this at some future point. I'll talk about why that's useful in the next couple slides. And then obviously the fourth type here, the second type of uncommitted memory, is free memory. Just the application's never accessed it, and most of the time when you start up a process, most of the address space is just free. Not reserved, not committed, but free. There's a number of performance counters available. So one of the things I'm going to try to do here is just put out references to performance counters, to ways you can see things in Task Manager and ProcessExplorer and Resource Monitor. I'm not going to actually go run perfmon to show you, but this is kind of a reference. So private bytes, if you see the term private bytes in perfmon or ProcessExplorer, that is private committed memory. That's that subtype. Virtual bytes in ProcessExplorer and in perfmon is the total of shareable plus private plus reserved. So in other words, this is the sum of the non-free portions of the address space. Take size of address space minus free, and you come up with virtual bytes. That gives you an idea of how much of the address space the process has used. When virtual size gets close to the address space size, the process is really out of its virtual memory. Of course, it's got potentially reserved memory that can actually go and turn around and use. But if it wants to allocate new blocks of virtual memory, it's going to be out of luck. Unfortunately, there's no separate counters for shareable or reserved or free. Let's take a look now at some of the other ways you can see the virtual address space breakdown in terms of columns. And this is where some of the confusion starts to get really obvious. Before Vista, there was a column called VM size. Anybody remember VM size? So VM size, the confusing thing about that is if you look at this perfmon counter in the previous slides, virtual bytes, virtual memory size seems like it should be virtual bytes. But in fact, in Task Manager and prior to Vista, it wasn't. It was the private bytes, a number of private bytes. In Vista and later, they finally changed it to commit size, which is still not quite accurate and doesn't align with what perfmon calls it. But it's at least a little bit better. You know it is committed memory. It's just not the shareable, or not the image and file-backed parts of committed memory. Unfortunately, Task Manager just doesn't quite ever get it right, and it flips between different terms over time. And try as I might, I haven't been able to find the Task Manager guy at Microsoft, because I really want to have a conversation with the guy. ProcessExplorer will show you both virtual size and private bytes. So let's do some experiments here to see some of these concepts in action. I'm going to do this inside of, I keep opening my terminal server system. Let's do it on, see if we can log into our Win7 system now that it's back. And run a few demos in here with test limit to show you the size of the address space. All right, why don't we use the XP machine then? By the way, I'm running these VMs off a USB key, so this is Hyper-V, but that explains why performance isn't exactly what you would hope. In fact, the performance is slower than, there we go, than I've experienced before. Let's get ProcessExplorer ready to go. And ProcessExplorer, by default, will show you the private bytes, and I'll explain why private bytes is so important here shortly. Let's go ahead and run test limit -r. I'm going to run test limit -r. What that does is says test limit, try to reserve as much memory as you can. I'm on a 32-bit system. And as you would guess, I'm able to allocate roughly 2 gigabytes, or reserve roughly 2 gigabytes of virtual memory. It's the address space on a 32-bit process. And then I'm going to do another thing, which is allocate private committed memory. That's test limit -m. And then let's go, and I was able to allocate, and I just got a little balloon, virtual memory minimum too low, but we're still being able to allocate. Let's go take a look now on test limit and take a look at both private bytes and virtual memory size. So virtual size, I've already got added, it's over here, and let's drag this over. So virtual size, remember, is the amount of the address space, total address space minus amount that's free. Uh-oh. It's not my fault. So what's happened there is we've run out hit a different limit, which we'll get to in a few minutes, and that is the system commit limit. Let's retry that experiment. And what I'm going to do is stop it here and run ProcessExplorer again. The system is going to be a little bit sluggish as we're waiting for this. As if it wasn't already sluggish. And why isn't this thing stopping? There we go. And let's see if there's enough virtual memory left for ProcessExplorer to get up and running. It's kind of, I really like to show you the case where the address space is fully maxed out, but what we can do if this fails to run is just try it on this system and try it with, and that's just taking too long. So let's do it on this system. I'm going to run test limit -r, and let's just allocate 100 megabytes of virtual memory. Oh, I meant to not do that. I meant to do 100-C1. So I've allocated 100, reserved 100 megabytes. Now let's do test limit -m 100 C1, and then let's go take a look at ProcessExplorer. And I've got virtual size and private bytes going, and where's my test limit programs? Oh, I've paused. There we go. Here we go. And if let me scroll this so you can see better what columns are what. So I allocated 100 meg. The virtual size is a little bit more than 100 meg because there's other stuff that test limit has allocated. That's DLLs and its file. If you look at private bytes, the reserved one is immediately obvious because it hasn't allocated any private bytes. It's simply reserved that 100 meg, which shows up in virtual size. But whereas the one that I passed with the test limit -m has actually gone ahead and allocated the whole thing and made it process committed. The reason that private bytes is so prominently displayed in tools like ProcessExplorer and Task Manager is that's where you're going to see process leaking memory. Private bytes, again, is its private data store. If you've got a leak, what's happening is the process is allocating virtual memory, using it for something, and then forgetting to free it. And eventually, you're going to see behavior like we just saw with test limit -m. Is the process itself blow up, or it caused the system to blow up? So private bytes, by looking at that, you can spot the memory leakers. If you see that value constantly going up, if you see it getting close to the address space size of the process, 8 terabytes on 64-bit systems. Actually, you'll never see it get that big on 64-bit systems because we'll hit another limit first. But if you see it growing, then you probably have a memory leak. There's another type of problem that can happen with address spaces, and that is address space fragmentation. This is the case when you're allocating memory out of the address space, and there's just not a big enough free block anymore for the process to make the allocation it wants. That allocation will fail. The application might not have anticipated it. Even though there's still free regions in the address space, the process is effectively, from its perspective, exhausted its address space and crashes. And address space fragmentation, again, is going to be an issue on 32-bit systems. Figuring out what kind of resources being hit here is something that the general performance counters won't show you. So I'm going to introduce another tool here, a Sysinternals tool called VMMap, which will let you look inside of a process with gory detail to see what's going on. And let's take a look at VMMap, and we're going to launch Notepad and take a look at Notepad's behavior with VMMap. Do a refresh here, and here's Notepad. There's a lot of information presented here. Let's take a quick look at some of these things, starting with these graphs at the top. This graph shows you committed memory, process committed memory, by the type of memory it is, with the types being defined in more fine grain than what I've just described. So we're diving into another level of detail here about how a process is using its virtual memory. Then if we take a look at private bytes, this is the breakdown by type. And the total amount of private bytes that Notepad's allocated thus far is 1.6 meg. The total amount of private committed memory it's allocated is 52 meg. Working sets have to do with physical memory. We'll cover that in a bit. Here at the top, what we see is the totals column shows us the total of each thing. So size is the total, is really the virtual size. That corresponds to ProcessExplorer's virtual size column. Total address space minus free equals size. The amount of process committed memory, or the amount of committed memory, both private and shareable, is shown in the committed summary. The total amount of private committed memory is shown here. And then we end up with working set stuff that we'll get to later. When we break down the types of use of an address space, there's images. This is where the process maps in DLLs in its own executable image. There's map files. These are the shareable memory regions that are backed by the paging file, or sorry, that are backed by a file on disk. If you click on one of these, then you can see down here details about the particular type of allocations of that type. Like I said, memory map files. These are files on disk that have been memory mapped as data into the process address space. Then we have shareable, and this is the page file backed shareable memory regions, which don't correspond to files on disk, which is why you don't see details over here. So that's kind of the shareable types of address space: image, map file, and shareable. Then we end up with more of the private types of virtual memory: heap, managed heap, which you're going to see in a .NET application, stacks, and private data. And then we have system stuff, page table, and then there's just stuff I couldn't figure out, so I'd lumped it all into unknown. Actually, there's, unfortunately, with analyzing memory usage, there's some dark holes. There's some dark spots, which it's impossible. There's no counters to actually get the sizes of some of these things. And so I infer the sizes of those things by taking the total size of the process, private bytes, subtracting what I'm able to see, and the rest is unknown. Really what that is, if you're really interested in the technical gore details, copy on write pages that have been split but then marked as read-only, and virtual address descriptor charges, so just charges for describing the process address space. And then we have free. This is a 64-bit Windows system. So we see that we've got close to that 8 terabytes free. Notepad's not done a very good job of using its address space. If we want to see the largest free block in terms of address space fragmentation, there's a free block that's almost that size and free, 8.581. So we don't have an address space fragmentation issue either. I talked about reserve memory, and you're probably wondering, what the heck would I want to reserve memory for? It's when the programmer wants to be able to have allocations that are contiguous with one another, but they don't want to do it all up front. This is going to be the case when their data set potentially grows, but they don't know necessarily how big it is. They only want to have the system pay the price for what's in use right now. There's a couple of great examples of use of reserve memory. The heap uses reserve memory because the heap allocates a certain amount of, or reserves a certain amount of virtual memory, and then starts allocating heap blocks from that. Each heap is managed as a whole, and the heap manager expects that entire heap allocation to be contiguous. So what it can do is commit parts of the reserve memory as the heap needs to expand. There's an even clearer example of why you want to reserve memory, and that's in the stacks. Every thread in the process has its own stack. This is Notepad. It only has one thread in it, and it's got a stack. And this is the breakdown of the stack's allocations. You can see there's 3 sub-allocations. And if we go over to the right, you can see what makes them different. One of them is read-write guard. One of them is read-write, and one of them is reserved. Actually, let me sort this by address. And you can see the read-write here. Stacks grow down. So the first thread, the amount of stack that's actually used is represented right there. Rough 20K, here the size, 68K has been touched by that thread. Then there's this 12K region, which is a guard region. This is an off-limits region, but if Notepad allocates more stack and it touches this guard page region, the system catches the exception, sees that it's a stack region with a guard page, and then we'll go and do what's called stack expansion, which means that what it'll do is move that reserved region up, committing part of the reserved area that you see right above it, and expanding the read-write region by committing, changing that guard area to read-write, and that lets the stack grow. The stack needs to be contiguous, which is why it has this chunk of reserved memory. So for Notepad's case, it's got 512K of potential stack. If it blows through that, the application is going to crash. So that's just an example of why reserved memory is so useful. One of the things that VMMap can do for you, too, if you're interested in tracking down a leak, or you're interested in what's the cost of this particular feature of this application, how much of an impact on the system does this particular operation, this client operation on the system, on the component have, VMMap supports differencing and snapshots. So let's see how much memory the file open dialog costs. Take a guess. 1 meg? 2 meg of private committed memory? 3 meg? 10? Lower. Lower? 512K? How many people say higher? How many people say 100 meg? Oh. Well, let's see. File open. So I'm just going to leave it like that. Press F5, and then do Control D to see the difference. So this is you'll see negatives if any of these values went down. If you don't see a negative, that means the value has gone up by that amount. The amount that has gone up private, bytes, 10 meg. How many people were in that range? Probably not very many of you, right? You don't expect, well, you know, the file open dialog is just so powerful that I actually spend most of my time in there. You can create files, create network shares, delete files, launch applications. It's no very any reason actually to go out to Explorer. You can see that we've brought in 40 megabytes of images. We've created 2.7 megabytes of map file. So you get the idea, and if you want to see exactly where those allocations happen, like heap allocations. Well, we've done a lot of heap freeze, but then we've done a lot of heap allocations, actually at the same addresses too, which makes a lot of sense. One of the things that's kind of concerning is the remaining impact of just opening the file open dialog. How much do you think the virtual memory, the process private committed, is going to go down once I close that dialog box? So it's gone up by 10 meg. How many people say 1 meg? 0. Somebody said 0. That would be bad. Let's see. F5. It's gone down by 3.5 meg. Remember, it went up 11 meg before, minus 3.5. So we're still at net positive 8 meg just from opening that, doing the file open dialog. I'm sure there's a good reason for that. In case we want to open it again, it doesn't have to do all that same stuff again, hopefully. So when I ran that experiment in the VM, where you saw ProcessExplorer crash, you saw that little balloon that said you need more virtual memory, that relates to another limit. I've covered at process address space and how processes use their address space, but the use of committed memory, private and shareable page file back memory, has an impact on the total system available virtual memory, which is represented with this term called the system commit limit. Remember, if the committed memory is backed by an image file or a data file, it doesn't count towards this. This is only data that, if it's ejected from RAM, would have to go to the paging file. That's the only type of data that counts toward the system commit limit. What is the system, where does the system commit limit come from? If you think about that kind of data, it has to be in one of two places. I said if it's ejected from RAM, it goes to a paging file. But it also could be in RAM. So it can be in one of the two places, RAM or a paging file. So right there, that tells you the total amount of system commit available on a system is the sum of RAM and paging files. Yeah, you can just read the slide there. That's good. So that right there, summing RAM, and I've got 2 paging files in that diagram, that is the total system commit. That's the system commit limit on this machine that I've got in that picture. And that means processes allocating that type of process committed memory, add them all up. When they hit the system commit limit, you're going to get that low on virtual memory. There's a number of different ways to go and look at where you are right now in terms of impact on system commit. One of the ways is with ProcessExplorer, which will show you the current, the limit, and the peak. And that's in the system information dialog down here. So the current commit charge, system commit charge, is 3.5 gigabytes. The limit is 7.8 gigabytes, and the peak, well, I've come really close, dangerously close to actually running out of virtual memory. I'm right now, you can actually see, I came within 8% of running out of virtual memory on this machine at one point. The current, I'm currently at roughly 50%, so I've got plenty of virtual memory right now. Prior to Vista, Task Manager shows it as page file usage and shows it in a graph up here. So this is on Windows XP system. Why don't we just go take a quick look at XP? Oh, I don't have the system thing here. What the heck? This must be Vista Home Edition or something. That's weird. Oh, maybe it's because I'm out of, sorry. You know what? I'm probably still running low on virtual memory. And Task Manager simply wasn't able to allocate the other tabs. So, yeah, the behavior of the system when it's out of virtual memory is pretty interesting. Let's see if we can get some other behaviors. Like, let's launch IE. Insufficient system resources. It's just kind of fun just to poke around and see what happens. I'm clicking on things and nothing's happening. Let's run FreeCell. We can get to it. You get the idea. When you're blocked from running FreeCell, the system's really in trouble. Now, the irritating thing about Task Manager before Vista is that it calls it page file usage. which is ridiculous because it doesn't really mean it's page file usage. It's really system commit. I'll show you in the next few slides, you don't even need a page file to run the system. But you'll still see this, even on a system with no page file, it still calls it PF usage. What that really is kind of saying is, again, if that data was ejected from RAM, it would have to go to the page file. Task Manager in Vista doesn't even show you a graph anymore. It just shows you that page file and commit megabytes. So we'll show you the current versus the limit. On Vista, it calls it page file. Finally, on Win 7, we call it commit, shorthand for system commit. So we're getting better about standardizing on the terminology here. And exhausting the system commit limit, you've actually already seen it. On any system, running test limit 64-M will exhaust the commit limit before it exhausts its address space. Again, its address space is 8 terabytes. You can't have 8 terabytes of virtual memory on your system. So you will exhaust that first. Here's a graph which shows you test limit running and exhausting the commit limit repeatedly. And you see this stair step right there. And you see test limit saying, I'm pausing for 5 seconds. I can't allocate anymore. I'm going to pause for 5 seconds. The reason that I do that is that paging files can actually grow. Most of you probably knew that. You can set a minimum and a maximum size for the paging file. And what that means is that when you're looking at the system commit limit, that is the system commit limit right now. That is RAM plus the current size of the paging files, not what the paging files could potentially be. There's no guarantee that the paging file can grow. You could run out of disk space, and the paging file wouldn't be able to grow. So it makes sense to show you what the commit limit is right now. Doesn't necessarily mean that you've got a problem, though, if you've got one that can grow, and that's something that's important to keep in mind. So how big do you want to make the paging file? This is the burning question. This is what we get paid the big bucks for. And everybody's got their theory. You go pull a man off the street and say, how big should your paging file be? And he'll say, 1.5x RAM, 2x RAM. I was reading a magazine, Windows magazine. It's the official Windows magazine, it turns out. It's based in the UK. I don't know why it's not based in Redmond. It's based in the UK. And they've got, how to tweak your system's performance. You know what? You know how big it says you should have your paging file? 300 meg, that's good. Or 600 meg if you really, want to have a big one. So everybody's got, and actually, these numbers are totally ridiculous. So what you should do is let the system manage your paging file, right? You can see in this, if you go to Computer, Properties, Advanced System Settings, Performance Settings, super duper advanced, change. You've got automatically managed paging files for all drives. So it sounds like, ooh, Windows is really doing some really smart stuff to make sure that paging file is the right size. You know what Windows does? If you've got more than 1 gig of RAM, it starts with a minimum of 1.5 RAM and grows up to 2x RAM. So yeah, it's really smart. In fact, the guy that did this, I guess, never got it out of a magazine, I'm guessing. Now, why is this number ridiculous? Well, I've talked about what contributes to system commit limit. That's the process committed pages from shareable page file back pages as well as private pages. It depends. It depends on your workload. What the applications are allocating of that type of memory, how much they're allocating. So a simple RAM formula doesn't make any sense from that perspective, and it makes even less perspective when you consider the fact that system commit limit is RAM plus the size of the paging files. If the workload only needs 2 gigabytes of system commit, and you've got 4 gigabytes of RAM, how big of a paging file do you need to support that workload? 0. The formulas, though, tell you 1.5x or 2x. Doesn't make any sense. How do you tell how much a workload needs? It's ProcessExplorer showing you the peak. And pre-Vista Task Manager showed you. Unfortunately, that number's gone now in Task Manager. Again, that Task Manager guy, I really want to talk to him. So the answer for sizing the page file is run your process under typical workload, go look here, and see what the peak has been. If on this system, if I expected this to be typical workload, I'd want to make sure that my paging file, or that my total system commit, was at least 8 gig. I've got 4 gig of RAM, so I need a 4 gig page file to support this, which I fortunately apparently do, and I was able to support this workload. Now, if you want to multiply something by something, because that, when you tell your boss you're doing important calculations and management of the system, then you multiply that number by something. Oh, and one more thing. The reason why you could theoretically run without a page file, given this information, that you would want to have a paging file, is so that Windows can take a dump when it's sick. No, that's the official terminology, by the way. I'm not just doing that to be funny. It needs to take a dump. And we call it kernel constipation if there's no page file. So that's one reason to make sure you have a paging file. Kernel memory dump's the default. Again, how big is a kernel memory dump? It depends on your workload. So you can use tools like Not My Fault or Outlook to crash your system. And just kidding. Figure that out. Let's talk about physical memory now and where those limits come from. Again, the limits here depend on a number of different factors. SKU licensing, whether you're 32-bit or 64-bit, what Microsoft tests on is a very important attribute, and the size of the kernel's address space has an impact on how much physical memory it can manage. One of the things I do want to make clear, I've just talked about virtual memory limits, now I'm talking about physical. People get the two confused. The only connection between one and the other is the system commit, because that's where RAM comes into factor. Otherwise, totally disconnected. Virtual memory processes virtual memory usage, totally disconnected from RAM, with the exception of that system commit limit, where that comes from. So just to make that clear. And by the way, that URL there tells you memory limits across all different releases. I'm not going to bore you with all that. I'll just cover some of the extremes, ends of the spectrum here. Physical memory on 64-bit systems, the kernel address space itself, the amount of address space it has to describe physical memory, limits it to 2 petabytes. That's the theoretic architectural max Windows could support. x64 page table structures, though, on current shipping processors, limit physical memory to 48 bits of addressability, which translates to 256 terabytes. So that's, today, assuming you had all the money in the world, that's the biggest kind of system you could put together. Windows would be able to take advantage of it architecturally, but not necessarily from a SKU limit perspective. Here you can see across different versions of Windows, low-end to high-end amount of physical memory support. Data Center, of course, supports the most that we would ever let anybody use. And where does that number come from? That number comes from purely what we can test on. This means that we've had a system with 2 terabytes of memory that we've actually tested Windows on. And so that's why we can say Data Center supports up to 2 terabytes. We haven't had anything bigger. 2 terabytes is pretty cool, isn't it? Now, this system that I showed you yesterday, it doesn't have 2 terabytes, but it's still pretty impressive. Anybody, can people see that? Let me zoom in here. Let me put some commas in for you. And remind you that you're looking at megabytes. Yes, that's 1 terabyte of physical memory on that box. And I always look for an excuse just to TS into that machine. It's just fun. Here's a picture of the 2 terabytes that we had on a particular machine. On 32-bit systems, the story gets a little more nuanced. Again, there's some SKU limitations depending on what SKU, or sorry, 32-bit server. The story gets more nuanced because we can't support, because of the system address space, more than a certain amount of memory. On Server 2008 R2, we don't even support 32-bit, so let's go back to Server 2008. The max was 64 gigabytes, and that comes from the fact that the system part of the address space, we've got to have this database called the PFN database, where there's an entry in it to describe each page of physical memory. And that has to be in RAM at all times. So, and mapped into the kernel's address space because of the architecture of Windows. And so on a system with 128 gigabytes, you'd need 890 megabytes of system address space for the PFN database. Again, the system address space is 2 gigabytes by default. You're taking 1 gigabyte of that away just for the PFN database in a system that's that large. That's why those caps were put in place, to let the kernel have enough room to breathe and do its thing and not have to spend all that address space on the PFN database. It's also why the limit is lower when you're booted 3G. Think about it, 3G, you've only got 1 gigabyte of address space for the system, limits your ability to create a PFN database in that. Okay, in client systems, that's where things get a little bit more tricky. It's based totally on licensing. 512 meg up to 192 gigabytes in Windows 7. The 32-bit client, though, is limited to 4 gigabytes. And that's by license and by the system just not letting you access more than 4 gigabytes. Why? We've had this problem with 32-bit systems where there's lots of device drivers out there for 32-bit systems. Tens of thousands written by really high-quality people. And one of the things they do is sometimes take shortcuts where they don't anticipate that the system's going to have more than 4 gigabytes of memory and keep their addresses as 32-bit addresses. If you've got more than 4 gigabytes, you need 64-bit addresses for RAM. So here we've got a system that's got 6 gigabytes of RAM. The device data is targeted at that region above the 4 gigabyte line. You can see that the low bit of that high D word is 1. But if the device driver truncates that and ignores that high D word, it's actually going to write the data to low memory and corrupt everything. The reason why we felt that it was originally safe to do this on servers have much more controlled population of device drivers, typically a lot more stable. Servers have had 4 gigabytes support for a lot longer than clients, and so that's why that policy is in place. In addition to that, you're really cheating yourself if you're running 32-bit Windows on a system that has 3 or more gigabytes of memory. And the reason why is that to keep all of the physical addresses below the 4 gigabyte line, device memory is also mapped below 4 gigabytes. And that pushes RAM above the 4 gigabyte boundary, so you can't access it. Here's an example screenshot of a system that I had at home that I bought from a high-end gaming company that shipped me 32-bit Windows on this system. It has 2 ATI GTX 280 graphics cards. They each have a gig of RAM. The window into this video memory is 256 megabytes each, so I'm consuming 512 megabytes of the address space, of that low 4 gigabytes, just for addressing the physical memory on those, or the video memory on those cards. So the result is I was cheated out of basically that 500K that I didn't have access to. The answer, of course, is to run 64-bit Windows on a system like this. Also, watch out for shared video memory. This machine that I'm on, I told you it was 4 gigabytes in size. Unfortunately, it's got a shared video memory card, which is consuming 256 meg of that total RAM. So the shared memory is actually something on top of, regardless of how much, whether you're running 64-bit. This is 64-bit Server 2008 R2, 4 gigabytes of RAM, but part of it is shared with the video card, effectively making it off use for general purpose use by Windows and really making it less useful for me. If anybody has a laptop you'd like to give me, it'd be great. Let's talk about working sets, physical memory usage now, as we wind down here towards the end. Just to take a look at how Windows manages physical memory. Every process gets a certain amount of physical memory that can grow and shrink over time as the demands of that process and other processes dictate. Basically, Windows tries to be as fair as it can in assigning memory usage. The way that a working set gets created is totally on demand. So a process, when it starts out, has no physical memory assigned to it. Its main thread of execution starts to touch pages of memory, and that causes these pages to get inserted in the working set. If you have plenty of available physical memory, the working set will just grow to accommodate all the pages that the process has touched, but that hasn't freed. So any active pages of memory that correspond to process committed memory that is currently active will be in the process working set. There's two types of pages in a process working set. There's private and there's shareable. Shareable, of course, goes with shareable virtual memory. Shareable virtual memory, images, shared memory sections. The point with that, though, is that just because it's shareable doesn't mean it's shared. If you have a process that loads its own private DLL, that's technically shareable virtual memory. And then if it's touching those pages of that shareable DLL, causing that data and code to be brought into its address, into its working set, that is technically shareable parts of its working set. However, if no other process ever loads that DLL, it's for all intents and purposes private working set. And there's ways to see from performance counters how much of a process's working set's private, shareable, and of that shareable, how much is actually shared. And you can see that with ProcessExplorer. So I've got those two test limits. I'm going to run another test limit. I'm going to add, here, let me switch to a different view. Load column set working sets. And let's sort by test limit. So I'm showing here private bytes, working set private, working set shareable, and working set shared. For these two instances of test limit, the one that allocated private committed memory, you can see that the working set for both of these is actually the same, because this guy allocated 100 meg, but he hasn't touched it. So he hasn't actually caused it to be added to its working set. It hasn't actually caused Windows to give it physical memory. Let's run another instance of test limit. And this one I'm going to run with the -D switch, which says allocate process private memory and touch it. And now let's go back to ProcessExplorer. And this guy, because he touched his 100 meg allocation, it's now in its working set. In its private working set, actually, if you look, because that's private physical memory. The shareable memory aspect of it comes into play with things like Notepad, where if I ran another Notepad instance, I wouldn't pay an additional cost in RAM for those pages that are shareable and shared between the two. A great example is notepad.exe itself. Most of that is code. This is why in a terminal server system you could have 100 people all running Notepad. There's only one cost for Notepad's code in memory. They're all sharing it in their working sets if they're running Notepad. And Windows keeps track of physical memory on a number of different lists. So what I'm talking about these lists for is so that we can understand how you measure the amount of available memory you've got, which goes into the question, do I have enough RAM on my system? There's working set lists, of course. Each process has its own list with its working set pages on it. There's the standby list, which is really the file cache. There's the zero page list, which are pages that have been freed and then zeroed by the zero page thread to be able to give them to a process zeroed already so they're not seeing anybody else's data by accident. The free page list, which are pages that have been freed yet not zeroed yet. And then the modified page list, pages that need to be written back to disk, either the paging file or a file on disk. The lists are implemented as entries in the PFN database. So the PFN database has these lists all weaving through it for each of these different things. And the memory manager watches activity to decide how to assign memory. The key value that we're after here is available memory. Available memories, the physical memory that the memory manager right now can take and give to a process without having to do a disk I/O. So which of these pages, which of these lists can it steal memory from without having to do a disk I/O? How about the standby list? Yes? No? Can it give that pages off the standby list to somebody? Yes. That's just cached file data. It can always go back to the file to get it. How about the zero page list? Obviously. How about the free page list? Yep. How about the modified page list? Nope. Need to do a file I/O first. How about working sets? Nope. Not necessarily. But we don't want to steal from working sets before we've actually tried to allocate memory from one of these other lists first. So right there you've figured it out. What is available memory? Standby plus free plus zero. And the order by which the system will try to allocate from if it wants to give a process more working set is kind of obvious. If it can give it a free page because it's immediately going to get overwritten by the operating system for example, in a disk I/O, it's going to give it a free page. Otherwise, it'll give it a 0 page. If it process needs a 0 filled page, it's going to give it allocate from there first. So the free or 0 page list, depending on what type of memory the process needs, it's going to go one or other of those lists first. And then finally, if those lists are empty, well, it has no choice but to start to eat away at the standby list, which is eating away at the cached file data in the system. There's a number of ways you can see the available memory counter. So XP Server 2003, you can see up on the top right. There's available, and then there's system cache. And system cache is actually standby list plus the modified list plus the system working set. In Vista and Server 2008, we've got cache now and free. So the available memory is gone, which was very useful. So the answer is on Vista, there's no way to see it on Task Manager. Now in Windows 7, it's back. Available is back. So we learned our lesson. The Task Manager guy, somebody must have talked to him. It wasn't me. Now in Windows 7, there's the resource monitor. How many people have run the resource monitor? So you've seen this probably in the memory list. Now here you get a nice graphical breakdown of the sizes of those lists. In use, which is working set, modified list, standby list, and free list. And ProcessExplorer, that's a screenshot of ProcessExplorer, shows you the sizes of the lists as well. I want to introduce very quickly another tool called Rammap. And Rammap will show you a very fine breakdown of types of memory, RAM in use. It's like VMMap except for RAM. So up here we see active, which is working sets, standby, zeroed, modified, and free. And then for each of those types of memories, it's broken down into how much of that active memory is process private, mapped file, and so on. So that's what this cross-referenced grid is. If I look here, out of that process private memory, there's 813 megabytes of process private memory currently allocated in RAM. 648 meg of that is in process working sets. 142 megabytes is on the standby list. You can see I've got driver locked memory, 1.7 megabytes. That's my virtual machines. This is how Hyper-V allocates RAM for the virtual machines. I've got remember, a 1 gig virtual machine and a 512, adding up to that number right there. So that gives you a really fine-grained look. Now, what's the burning question? Do I have enough RAM? If it's your boss asking, no. It's always no. But if you're really trying to size a system, there's no surefire way. There's no metric you can go look at. There's no counter you can just go look and see, oh, yep, this counter says need more RAM. There's no perfmon counter. So Dave and I have spent a lot of time thinking about how do we come up with some way to give people some guidance on this. The way we've come up with is the general rule, is available memory low, continuously low? Because if it is, that means you're not letting the system build up a file cache. You're always running on the edge of physical memory usage. And adding more RAM probably, not definitely, but probably will help the performance of the system. And there's another way you can kind of indirectly tell if you need more RAM, and that's to monitor file activity on your server or system to look for excessive reads from the paging file. The reason why we say reads and not writes is that stuff gets written to the paging file. If it's never referenced again, you don't necessarily have a problem with RAM. But if stuff gets shuffled back and forth between the paging file all the time, you've got a RAM problem. Because stuff gets referenced in RAM, kicks other stuff out. Now that other stuff needs to get referenced, kicks this stuff out, pulls that other stuff in, and that's where your really performance is going to stink. So that's the other way to kind of gauge whether you need more RAM. So that brings me to the conclusion of the talk. I hope you've gotten some good advice and some understanding of the way Windows uses virtual memory and physical memory. You know how to track down handle leaks now. Got some basic terminology. I've got these slides serve as reference, so when you're working on a Server 2003 system, you can look at Task Manager and know what you're looking at. You can look at ProcessExplorer and know what you're looking at. Again, I want to point you at the blog where I've got a bunch of other posts on these other limits that build actually on the physical and virtual memory limits, which is another reason to have this as kind of foundational work. And Obviously, knowing this stuff is just going to make you a better systems administrator. If nothing else, you know how to size the paging file now.